And thank you to all of you for being here to listen to me. This is pretty awesome. And thanks to the organizers as well. Plug this in. We'll hope that pops up. I think something's happening here. Cool. Yeah, so this is my fourth SciPy. I first came in 2012, and it's awesome. I kind of echo a lot of what Stefan said about this community. It's a great place to be, and I think Fernando said that in his keynote a couple of years ago, said coming to SciPy feels like coming home, and in a lot of ways, it is that, because these are our people here, right? And today I have the privilege of talking about the state of the stack. So talking about kind of a high-level view of what the SciPy stack or SciPy ecosystem, where we've been, where we are right now, and where I think we're going. And this is a huge topic, and I want to, at the very outset, I want to apologize, because there's going to be a lot of amazing things that I ignore in this talk, because number one, because I don't have time, and number two, because I probably just don't know everything incredible that's happening out there. So if I ignore something in the talk right now, just forgive me and tweet at me, and then we'll make sure the world finds out about it. The first thing I want to do, though, is I want to thank the sponsors. So I'm working at the East Science Institute at the University of Washington, and we're funded by the Moore Foundation, the Sloan Foundation, the Washington Research Foundation, and the NSF. And it's really because of the opportunities that these sponsors have given us that I'm able to spend a lot of time writing code and writing blog posts and thinking about big picture things. So I'd really like to thank them. And also I want to highlight that the Moore and Sloan Foundations, along with the Helmsley Foundation, if you didn't hear this week, they just granted the IPython project, the Jupyter project, $6 million to continue development. So I think we should thank them. Because it's foundations like these that really help us continue to produce these kinds of tools. So anyway, in this talk, I want to just talk about three quick things. I want to talk about where we are as a community, where we're coming from, the history of how we got where we are, and then based on that history, I want to speculate a little bit about where we're going and kind of offer some framework to think about how we as a community can move forward. So let's start talking about where we are. The Python scientific ecosystem. Of course, it's built on Python as a foundation, right? And on top of that, we have this core of scientific tools that really helps drive everything else that happens. And in particular, NumPy is our core numerical computing language. We have Cython, which bridges the gap between Python and C, and then we have this IPython and Jupyter projects that kind of tie everything together and give us a nice framework to work in. Now, on top of these, there's sort of the peripheral of that core. SciPy, which depends on NumPy. It has all the scientific tools. We have Matplotlib for visualization, Pandas for DataFrames, SciPy for symbolic manipulation. If you're into Mathematica and you like doing integrals symbolically, SciPy is a great package. And as of maybe 7 or 8 years ago, this core was maybe the extent of it. But we have a lot more tools now that are built on top of these core tools. Things like the scikits, scikit-learn, stats models, scikit-image. We have PyMC, which does some great Markov chain Monte Carlo Bayesian computations. Things like NetworkX for network analysis, PyTables for interfacing with large data sets. And as we go further up the stack, we find tools that are very domain specific. And here, I could write hundreds of different tools out here that folks in this room have developed, but some of the ones just as examples are the AstroPy project for astronomy, the BioPython project, and then things like NiPy and DiPy and neuroimaging, and so many more, right? So we have the reason this community works is because we have this huge extensive stack of software that we can use. And chances are, if you're trying to solve a problem, there's some tool in Python that'll let you do that. And there's many more that I didn't add the logos for, but just to throw them out there. For performance, we have things like Numba and Weave, NumExpression, Theano, that allow you to connect Python to low-level tools that will do really fast computation. Visualization, there's a whole cloud of libraries out there that does various forms of visualization. It's Bokeh, Seaborn, Plotly, Choco, MPLD3, ggplot, MayaV, Vincent, Toyplot. I learned about HoloViews this week, which is a really slick library. You should check that out. And then things for data structures and computation, trying to move data into distributed computation or parallel computation or that sort of thing. We have tools like Blaze and Dask out of Continuum, DistArray, X-Ray, I'll talk about some of these, GraphLab, SciDBPy, PySpark, these are database interface tools, so there's a lot of stuff there. And then of course the kind of the important but unspoken thing is the packaging and distribution. pip, Conda, Canopy, some of these tools have been really important. So that's just a broad overview of what we have. And I want to highlight a few recent-ish developments in the community in case you haven't heard about them, things that I'm really excited about in particular. So number one, recent-ish development is the core language. And I'm just going to put that up there. If you haven't changed to Python 3, now's the time. Most of the packages, I'd say almost all the important packages are there with Python 3 support. I work in Python 3 every day, and I have for about a year and a half now. And it's the switch is relatively painless. So it's time to move forward. I wouldn't have said that 2 years ago, but right now it's time. In the visualization front, there's a lot of interesting recent things happening. We heard yesterday in the State of Matplotlib talk about some of these. So some of the things I'm excited about, in 1.4, Matplotlib has these style sheet features where you can basically choose a new style for your plots. And in 2.0, Matplotlib is going to move forward with that and actually have new default styles. So the next release of Matplotlib, things are going to look a lot different, which I think is a really exciting thing. And as an example of how you can do this, if you use the standard Matplotlib styles, this is what something looks like. I created a function that just makes a histogram and several lines just to display some of this stuff. But you can use this plt.style.use command, and that'll load a new style sheet. So here, for example, is the built-in ggplot style. So if you're a fan of R ggplot, you can just use the ggplot style with Matplotlib, and it just works. Or there's the 538 style, which takes after Nate Silver's popular blog, with kind of thick, bold lines. And if you want to make 538 style plots, it's easy. The BMH, which stands for Bayesian Methods for Hackers, after Cam Davidson-Pilson's book, you can make plots in that style. So there's cool things. Another thing that's happening in the visualization space is this package called Seaborn, which kind of came on the scene in the last couple of years. And it's really surprised me how amazing it is and how much uptake it's had. And the idea is simple. It just uses Matplotlib not as an interface, but as a backend. And it defines its own API for domain-specific plotting, in this case in statistics. And it creates a really nice set of plotting tools. And one of the cool things about Seaborn is it added on a lot of these really nice styles for Matplotlib. So one thing, it's pandas aware, so you can use pandas data frames with it. But it has this beautiful, well-thought-out style, and one of the ways that I use Seaborn most often is I just import it and do seaborn.set, and then all of a sudden your plots are in this Seaborn style. And even before the Matplotlib style sheets, this is what I was doing most of my plotting in. If you look at the most recent astronomy paper that I wrote, all of my plots are in Seaborn style in this published paper. So this is great stuff. I'm really excited about this. You don't need to tweak plots by hand anymore. Another recent plotting thing is this Bokeh library, which I'm sure you've heard about. But Bokeh is really cool because it plots in HTML5. So it's in browser, and it has all these tools for flexible interactivity in the browser. It handles large data sets really well. That's one of the reasons for the HTML5 versus D3 choice. And an interesting thing about it is Bokeh is fundamentally a JavaScript library, right? So you serialize your plot data and metadata in some sort of like JSON structure or something like that. And there's a JavaScript library that interprets that and plots it. So it means that there are Julia bindings to Bokeh. It's not just Python bindings. And what the Python API does is it generates this serialization that's then visualized by the library. So it's a pretty cool approach, and I'm fairly excited about this project. So recent developments in arrays and data structures, this X-ray project is quite interesting. You know, it kind of takes the best features of pandas and sticks it into NumPy, so now you have labeled n-dimensional dense arrays. And it really strikes me that this is kind of the approach that we want to move towards, because data today, it's not the 70s anymore. We're not working with anonymous dense arrays of data. We're working with labeled data, we're working with heterogeneous data from different sources, we have missing values, and NumPy just doesn't handle that. But tools like Pandas and now X-ray are moving in that direction, and I think it's a pretty exciting thing to see what will happen. Another one, I've just heard about this recently, is the Dask system, and I love this because it takes all the infrastructure that we've built for NumPy and Pandas and wraps it with a simple layer that generates task graphs, and then all of a sudden you can do NumPy and Pandas computations in parallel, multi-threaded. And it's this beautiful little system. You know, it's a lightweight package, but it's doing some really, really cool things. So I'm excited to see what's going to happen with that in the next couple of years as well. So some recent developments in computation and performance. You may have heard of this Numba package. And the cool thing about this is what Numba does is it takes your Python code and it can compile it down to LLVM bytecode. Just in time compile your code, and then you end up with faster execution. So here's a simple Fibonacci number generator, right, for 4 lines of code. And you time it, and it takes 4 milliseconds or 4 microseconds to run, right? All you have to do is add a little decorator on top, this numba.jit thing, and then all of a sudden you have a 20 times speed up in executing your code. So this is a really silly example, right? But when you start doing large array-based computations compiled into LLVM with Numba, you can do some really interesting things. I had a blog post recently where I actually tried an algorithm, the non-uniform fast Fourier transform, and did a Numba implementation and found that it was able to get within about 25% of the speed of a 10-year-old Fortran library that's been, optimized over the course of years. All we had to do is add this Numba decorator and do a few other things with the function. So I think this is a really exciting thing that's happening in the field right now, in the stack right now. In distribution and packaging, I should point out this Anaconda thing, and especially the Conda command line tool. If you are not using Conda to manage your environments for development of Python, I think you should seriously think about checking this out, because it's like pip, the thing that's built into Python. It grabs packages for you, but it can handle non-Python dependencies. It's like virtualenv that's built into Python 3, but it actually has separate environments for binaries as well as for Python scripts, and it does things really cleanly. And you can think of it kind of like if you use Homebrew or Mac ports on your Mac. It's a lot like that, except it's multi-platform. So for things like teaching, software carpentry, you no longer have to worry about your students having Linux or Mac or Windows. You can give them the same Conda commands, and it installs the same software. So it's really, really nice tool. And this, I say without hyperbole, this has changed the way that I do research, that I develop code, and that I teach in the last couple of years. It's an amazing tool. And of course, I should say something about IPython and the Jupyter project. And the cool thing about the IPython project is this is something that's homegrown in the scientific Python community. And now it's branching out, and you have people in the R world, people in the Julia world, and people in other scientific environments that are using the Jupyter Notebook, which is this kind of general platform for scientific computing. And watching this project over the last 10 years has been pretty incredible. It's grown by leaps and bounds. And with the $6 million of funding coming up for the next few years, I can't wait to see what the team does. And there's so much more. Like I mentioned, there's all sorts of stuff. If you've been to the talks this week, you'll see all the tools and all the things that are being developed. And I wish I could do justice to all of them here, because it's just an incredible amount of stuff that's happening. So that's where we are right now. But it was interesting to me to think back on the historical perspective of this. Like, how did we get to where we are right now? When I talk to students that I'm teaching at UW, people see Python as this ecosystem. It's this thing that you install and you use, and it's just there, right? But the scientific ecosystem hasn't been just there for the whole time. It was developed by people, and the development is interesting, you know? If you look back on Python as a language, it was created in the 80s by this dude, Guido van Rossum, and it was created mostly as a teaching language, and basically he wanted to bridge the gap between shell and C. There's this interesting interview that I have a link in the bottom corner, The Making of Python, where he talks about how he used to use shell scripts for various things, he used to use C code for various things, and he wanted something in the middle that could kind of do the best of both, and that's why he created Python. And he's actually said that in the beginning, he thought that we would be writing small Python programs, 10 lines, 50 lines, and maybe a 500-line program would be a big one. And you know, I think some of these main projects here now are in the tens or hundreds of thousands of lines now. So it was really, really anticipated. And this is kind of a weird thing, right? Because Python was not developed as a scientific program language. And I would argue that Python itself is not a scientific programming language. Yet we have 600 people here who use Python for scientific programming. So how did this toy language become core of this stack that all of you and thousands of people around the world are using? And I don't know, in 1989, I don't think anyone would have predicted this outcome for the Python language. And what it really goes down to is that Python helped people with the workflow that they were using. So I went back and took a look at what some of the early creators of Python did before, early creators of the SciPy stack did before Python was around. This is John Hunter, and he said a few years ago in the Keynote, I had a hodgepodge of work processes. I would have Perl scripts that called C++ numerical routines that would dump data files. I would load them in the MATLAB to plot them. After a while, I got tired of that dependency, so I started using GnuPlot. Right? So it's just hodgepodge of tools that he's using, and he has this weird workflow. Fernando Perez was the same. He said in email to me a little while ago, my advisor had a heavily customized awk-sed bash workflow to manage job submissions and post-processing of C codes for supercomputing runs. I used her scripts to run my jobs, and on top of that, I added my own layer of Perl plus GnuPlot, IDL, and Mathematica. Right? And this is just sounding like a nightmare to me right now. Like, try to do reproducible science in that context, right? How do you do that? Travis Oliphant, who created NumPy and helped create SciPy, said, prior to Python, I used Perl for a year, then MATLAB and shell scripts and Fortran and C++ libraries. And he said, when I discovered Python, I really liked the language, but it was very nascent and lacked a lot of libraries. I felt like I could add value to the world by connecting low-level libraries to the high-level usage in Python. So that's essentially what all these people were doing. They were connecting the low-level libraries, all this hodgepodge of tools they were using, to a nice high-level interface that allowed them to do everything in one place. So, you know, Python is not a scientific programming language, I'm going to say that, but Python is a superb glue for all the scientific things that we like to use. So what Python does is it glues together this hodgepodge of scientific tools, right? And what Travis was getting at when he said that to me in the email is that this high-level syntax is wrapping these low-level C and Fortran libraries, which is where most of the computation happens. If you look at SciPy, what SciPy originally was, it was just a bunch of Python wrappers on the netlib Fortran libraries. We think of SciPy as a Python package, but it's not Python, it's Fortran. You know, Python is just the wrapper on top. And that's changed a little bit in recent years. There's been a lot more development kind of on the Python tool side in SciPy. But fundamentally, you guys are all Fortran programmers. You just don't know it. The real key here is that it's the speed of development that drew people to Python, right? It's not the speed of execution in Python. It's the fact that you can do things and try things really fast in Python. And especially when that Python is tied to these low-level libraries that do that heavy lifting, you can do some incredible things, as we've all seen this week in the talks. And so with this in mind, you know, I often run into people who ask this kind of question. You know, why don't you use C instead of Python? It's so much faster. This is mostly old school like physicists that I run into that, still have their stack of code that they've been using for decades. And I think the best answer to that kind of question is this: why don't you commute by airplane instead of by car? It's so much faster. And it's true, once you start running the C code, it's way faster than Python. No one's gonna argue with that. Once you get in the airplane, you're traveling 10 times faster than a car. No one will argue with that. But it's that process of getting to the airport and walking through security and compiling your code and checking for type errors and doing all this that really causes it to be slow. So for day-to-day tasks, you're not flying an airplane to work, and you shouldn't be using C for your scientific coding. But all this efficiency, of course, depends on this scientific stack that I've sort of outlined, right? So the question is, how did this develop, right? This wasn't something that God dropped on us in 2006. There was this long line of people working on tools, trying to solve their own problems that led us to where we are right now. And Python started, or the scientific stack sort of started with this early numeric code base. And numeric is basically what we think of as NumPy today. It was a Python wrapper on C and Fortran arrays. It was written by Jim Huguenin, and it was the early thing, and for a long time, numeric was what was there. And then somewhere around 1998 or so, this guy named Travis Oliphant came in, and he started using numeric, and he was using all these C and C++ and Fortran libraries, and he realized that I can use Python as a glue for all my process of computing. So he started building these wrappers for these Fortran libraries that he called multipack, and it was built on numeric. And this was the basically early version of SciPy. Now, in the meantime, some folks came along, and Perry Greenfield, who's here, who introduced me, is one of them, and created this project called NumArray. Now, the problem was that numeric was really, really good for small vectors, but as you started moving to larger data arrays, there were some issues with it. Like, it did some data copying, and it did some transformation of D types implicitly that wasn't really the best. So Perry and a few others decided that they were going to create this NumArray project to fix all those things. Now, this was kind of an issue, right? Because all of a sudden you have two array computing libraries. And I was talking with Chris Fonsbeck on our Bayesian run this morning, and what he said is that he remembers back in the day where you would get to work each morning and you'd think, am I going to use NumArray or am I going to use numeric today, right? You had to make that decision. And this was a real issue, and it threatened to split the whole community. I mean, I imagine we could have been in the situation where we had a NumArray SciPy conference and a numeric SciPy conference, but we don't, and the reason is because Travis came along and he unified these, and I still have no idea how he did it. And the people that I talked to who knew about NumArray and numeric are still baffled that he was able to do this thing. So it was this Herculean effort, and he united the best of both packages into this package NumPy. So NumPy is, as you know, what most of us are using today. And in the meantime, Travis and Eric Jones and a few other people got together, and they spun multipack into this package called SciPy. And SciPy, what it wanted to do was take all these packages in multipack and put it into a computing environment like MATLAB, where you could start doing real computational workflows without leaving Python, which is kind of a cool thing, a Python MATLAB replacement. And I heard Travis told me that originally he thought he wanted to call it PyLab instead of SciPy. So this might have been the PyLab 2015 conference, except they made a different decision. And around the same time, completely independently, this guy named Fernando Perez, who was a grad student in Colorado, started the IPython project. He basically wanted a Mathematica-style framework, IDE, for using Python. And he worked on that for a while. And in the meantime, John Hunter started, he also wanted to do MATLAB-style stuff in Python. So he created Matplotlib, which had plotting, it had kind of a shell thing, it had some computation. It was meant to be this MATLAB replacement, right? And there's all sorts of other things that have happened. Like in 2012, the IPython notebook came along, and it's this great project, as you all know, it's really changed the way a lot of people have done their scientific computing. 2009, we heard yesterday from Wes McKinney about the creation of Pandas. And Pandas, I don't know if it's really been appreciated, but I think Pandas is responsible for a huge part of the growth of the Python community in the last few years, I think. If you look at the number of businesses and tech organizations that are using Python, I think we can trace a lot of that back to Pandas itself. So Wes deserves a lot of accolades for his role in that. He's single-handedly grown the Python community by leaps and bounds. And then in around 2009, the notion of the scikit came around. And this was born out of discussions in the SciPy mailing list where people said, SciPy is way too big. I want to put a new tool in there, but it takes way too long to get a patch accepted. How should we do this? And people thought, well, why don't we have these scikits, which will be like add-ons to SciPy that are sort of vetted by the community and developed independently. And out of that has come packages like scikit-learn, scikit-image, stats models, which I believe used to have the scikit moniker in there as well, and other scikits along the way, which are not quite as well known. And then finally, I mentioned my gushing love for Conda, and Conda was released in 2012, which is relatively recent in this whole thing. But this is kind of the overview of the history of the tools we have. And the thing that I want you to realize from this is, like I said, this ecosystem was not dropped out of the sky into our laps. It was developed over the course of time, and it was developed in a really federated manner, right? Everyone kind of does their own thing, tries to solve their own problems, and then eventually via Twitter or however else, those packages, people find out about these packages and start using them, right? And it's federated, and the analogy I like to use is that Python is federated sort of the same way the United States is federated, right? We have all these states that are sort of doing their independent things, and and the only reason that the United States does things together is because you had like these great folks early on who pulled together all these competing ideas and kind of unified them, right? And got everyone on the same page. And in Python, we've kind of had the same thing, right? So we have our George Washington, which is Travis Oliphant, we have Eric Jones and John Hunter and Fernando Perez and all these other folks who have done the hard work of uniting this federated ecosystem of packages. And as a result, if we look at some of the history, like I love these old package logos. I had to dig really deep to find some of them. This ketchup and mustard Matplotlib logo is beautiful. But if you look really deep, like Matplotlib and SciPy were both started as essentially full-stack MATLAB replacements. And they had everything. They had visualization, computation, some sort of shell solution in there. IPython was started as a full-stack Mathematica replacement. That's what Fernando was trying to do. And you kind of see why he ended up with the notebook eventually. That was his goal since 2001. He wanted a Mathematica replacement in Python. And through blood, sweat, and tears, he's managed to do it, which is pretty awesome. And it took this kind of communication between these folks and the SciPy conference, which started in 2002, and other meetings along the way, to realize that what we need in our modern stack is not a bunch of competing tools. We need tools that are complementary and work together. So this didn't happen by accident. That's what I want you to know. These tools working together, it was a deliberate decision over years and years of folks meeting and working together. And that's why we have the stack that we have today. So thinking about that, I want to think about what we can learn from this history of where we've come from as a community as we think about the future and how we're going to move forward. So some of these lessons learned from the story that I hope I've told well is, number one, there's no centralized leadership, right? There's not a dictator in the SciPy community who's going to tell everybody what to do. We are a bunch of scientific researchers, we're a bunch of data analysts, data scientists who need tools to solve our problems, and sometimes we write new tools to solve our problems. And the interesting thing about that is that core system that I laid out that tree of Python and then NumPy and SciPy. That core system is it's always up for question. We can always decide what we want to push in the core, what we want to pull out, how we want to modify that. So one example of this is I'm wondering if we should start thinking as a community about pushing Numba into this core next to Cython. So a few years ago, Cython was still a newcomer, and now SciPy is built on Cython, you have pieces of Pandas built on Cython, you have pieces of scikit-learn built on Cython. It's become this core package. And I'm really excited about Numba because it offers this kind of new thing, this LLVM just-in-time compilation. And I I think about what SciPy might look like if we start using Numba at the core of it, or what Matplotlib might look like, or what scikit-learn might look like if we start treating Numba as this first-class core thing. And admittedly, Numba has a long way to go. There are a lot of things that are still feature incomplete about it. But one of the exciting things, I was talking to some of the Continuum folks, and they told me that out of all Continuum's open source projects, Numba is the one that has the most community uptake as far as development effort coming from outside of Continuum. So Numba is not a Continuum project. It was started by Continuum, but it's an open source project, and it has people all over the world working on it. And I think we might progress as a community if we stick that at the core next to Cython. Another lesson from all of this, to be most useful as an ecosystem, we have to be willing for these packages to adapt, right? We had to pull plotting routines out of SciPy because Matplotlib did it better. We had to pull computation out of IPython because SciPy was doing it better. And one way we can adapt to the changing landscape is maybe think about pushing pandas to the core next to NumPy. You know, I think I said when I was talking about X-ray that modern data is heterogeneous, modern data has missing values, modern data is sparse, and Pandas handles this a lot better than NumPy. And I really think we should stop treating the data frame as an add-on. And for an example of what we might do with this, well, X-ray might be the solution to this. I'm not sure right now, but we can think about that as a community. An example of where this might go, consider if you're plotting the data in a data frame using Matplotlib's API. You have this plot command, you do the xlabel command, you do the legend command, but you have all this repeated information, right? The time is there, the temperature is there twice. If Matplotlib depended on pandas, if pandas was a core dependency, you might be able to do something like this. plt.plot time, temperature, and data. You just pass the name of the columns you want to plot. And you know, it would take a little bit of hacking, but I think you could make the entire Matplotlib package work this way, where a data keyword gives you the data frame, and you just pass the name of the column for whatever data you want to pass in. So we could really do some interesting stuff with that. Another thing, if pandas was a core, we could start moving pieces of Seaborn, which depend on pandas, and the plotting functions within pandas itself into Matplotlib and kind of reduce that overlap between these core packages. So I'm not saying this has to happen. You know, like I said, there's no dictator, but this is something that I think I'd like the community to think about and consider. Seaborn, I think, will live on as a package in itself because it has such awesome domain-specific plotting routines, and I'm just so impressed with what's been going on in that library. Another evolving core thing is thinking about SciPy. I was listening to Travis's Euro SciPy conference keynote from last year, and he said in 2001 we came out with what we called the SciPy library, but it was really the SciPy distribution. I didn't realize it at the time, but that's really what it was: a collection of tools with a single installer, so you can get everything up and running quickly. So what really motivated this monolithic SciPy package was the fact that packaging in Python is broken. And I would assert right now that packaging in scientific Python is no longer broken. Conda has solved the problems. So do we really need SciPy to be a monolithic package? If you want to use the integration tools in SciPy, do you need to install the interpolation tools and the special functions as well? There's been some chatter on this on the mailing list going back 4 or 5 years, but we might think about breaking up SciPy into its components. I'm not saying it's the best thing, but it's a conversation that we might start. Another lesson learned. So interoperability with core pieces of other language has been the key to the success. I talked about Python as a glue, not as a scientific computing language. So Python wraps all these C and Fortran libraries, and you have tools like Jupyter that are starting to be cross-language and more polyglot. And if you look at, one lesson we might draw from this is thinking about plot serialization. So if you look at the package that I wrote, MPLD3, which you might have seen, essentially it's a gigantic hack that outgrew itself. And what it does is it looks at Matplotlib and it crawls the Matplotlib object structure to produce a JSON serialization of the Matplotlib plots with all the information, all the data and metadata you need. There's this 2,000 or so line MPLD3 JavaScript library that reads that JSON file and turns it into an interactive online plot, right? So this might ring a bell, because I mentioned earlier Bokeh does kind of the same thing. It produces a serialized plot representation. It has a JavaScript library that then displays the plot in HTML5. So the question is, what if Matplotlib itself could do this kind of serialization natively? And this is a discussion that started about a year ago at the last SciPy conference, and I was really pleased to see in the State of SciPy talk yesterday that they're really pushing on this idea of serialization for the next release of Matplotlib. Because what it tells me is that you might be able, once you can serialize your data and metadata for your plots, you can do anything with it, right? You could use VisPy to render it in OpenGL. You could use Bokeh to render it in the browser. You could even use R's ggviz, because ggviz is based on the same kind of idea. It's like a JavaScript library that ingests some data. So the possibilities of cross-language collaboration are pretty endless. And I really think in this, IPython and the Jupyter project has led the way. You know, Jupyter, I think, is going to become this uber scientific notebook that just everyone uses and uses in every language. And it's why Fernando has worked hard to hire one of the Julia developers at Berkeley and have them nearby to collaborate on this. Another thing that we might think about is universal DataFrames. So, you know, whether you're in R, Python, or Julia, your arrays are these C or Fortran memory blocks that everyone's been using for the past 30 plus years. But in the case of DataFrames, it's very different. You know, R has their own DataFrame representation. Python has pandas. Julia has DataFrame.jl. There are a ton of these implementations out there, and we're really missing, I think, an opportunity by not relying on some core tools between these languages. Like, for example, it's hard for Julia's DataFrames to communicate with Pandas DataFrames because they're just fundamentally different. Whereas Julia, when working with C or Fortran dense arrays, you can pass them back and forth between Julia and Python with no problem, right? So the question is, could we create some sort of Uber DataFrame representation? And I guess this is not in the sense of Uber of DataFrames. I mean it in the sense of the word Uber before the company Uber disrupted the English language. But yeah, could we create this Uber data frame that that everyone uses? I know it's kind of, there's this XKCD comic of like, you know, there are all these different. I should have put it up here. I just thought of it right now, man. There are all these different standards. We should create another one to unify them all, and now there are all these different standards plus one, right? But maybe we could do it. Maybe we could do it. And I will say there are actually people whose names you know that are thinking hard about this and are considering meeting with folks from other languages about this problem. So the fourth lesson that I want to leave you with is that the stack was built from both processes of continuity and processes of breaking change. So the continuity example is this numeric numarray turning into NumPy thing. Travis was able to do this and kind of continue the legacy of old code and spin it into something new that's been long-lasting. But there's also these breaking efforts, these brand new efforts, and examples of those are Matplotlib itself and Pandas. You know, Wes said yesterday that when he was starting Pandas, there were a lot of people telling him, oh, you know, you should just work with the NumPy package and try to modify it for what you need. There's no need to do something new, right? And John Hunter talks about, in his 2012 keynote, he talked about the first time he presented Matplotlib at a SciPy conference. And apparently Robert Kern himself raised his hand and said, why are you creating another plotting package in Python? We already have so many, right? So sometimes this breaking change is a good thing, sometimes continuity is a good thing. And so for an example of this, considering the future of Matplotlib itself, there are all these complaints about it. Matplotlib is a almost 15-year-old library now, and it's showing its age a little bit. And there are things like non-optimal style defaults. There's non-optimal API. People like to complain about this in the context of tools like ggplot. There's difficulty exporting interactive plots and interactivity in general, difficulty with large data sets. But this continuity thing is starting to bear fruit, right? I talked about Matplotlib 2.0 with new style defaults. We're modernizing Matplotlib right now. This non-optimal API, we can have wrappers like Seaborn, and there's this ggplot library out of Yhat that uses Matplotlib as a backend with a new API on top of it, and it's an interesting way to move forward. This exporting interactive plots, I think we're almost there. If this serialization thing comes to the front, then all of a sudden MPLD3 will no longer be a hack, and we can actually turn it into a feature-complete package. And we can think about targeting bokeh with Matplotlib and things like that. So I think the interactive plots thing is almost solved. We're getting there. But we still have this problem of difficulty with large data sets, and I don't know whether this is something that can be handled within Matplotlib as a continuous thing, or whether it will need a breaking change. Will it be the Matplotlib developers who figure this out, or will it be one of you sitting in this room who decides to set off on your own, and in 5 years, you're the new John Hunter? I'm not sure. So the lesson from numeric and numarray is we should stick with Matplotlib and modify it, right? Maybe serialization to VisPy, we could do something like that. And Numba-driven backends, maybe that would work. Some sort of new backend architecture, I don't know. The lesson from Pandas and Matplotlib itself is that, screw what everyone else is doing. I'm going to build my own tool and become world dominant, right? And there's some examples of this. VisPy is doing some awesome stuff. Bokeh is, as I said, is a great package. Or it could be something new that no one has heard about yet. So with that in mind, what I want to leave you with is I've been talking about the state of the SciPy stack. And I want to leave you with this. The state of the stack is up to you. Thanks. Yeah, so we have time for a few questions. Yeah, right there.
So you mentioned the possibility of putting pandas into the core in order to enable the stack to be more label aware. But I wonder, what's your thought on what that would do in terms of making the stack more time aware? And also, more generally, what you think the possibilities are for making the stack unit aware, which seems like kind of a logical place to go for scientific.
Okay, so the question was putting pandas into the core would make the stack more label aware. Could it make it more time aware, and could it make it maybe more unit aware? I haven't thought much about that. I've been thinking about pandas in the core mainly as a label thing rather than as a time series thing. It might be that pieces of pandas go into the core, and that the time series functionality is sort of this special build-on that is still kind of outside. On the unit-aware things, the thing that I know that's going on with units, the best solution I've seen is actually part of the AstroPy package. So if you're not an astronomer, you might not have dug into this, but AstroPy has this astropy.units framework, and it's really, really slick. Like you can do full dense NumPy arrays with units. And if you take a distance array and you divide by a time array, you get a velocity array. And the AstroPy units framework knows that. So I would check that out. And you're right, it might be that something like that is important enough that we could think about it spinning off into its own core piece that other libraries would depend on. It would be difficult because there's so much legacy code, right? That's always the challenge. But at least if you want to use units, that's a solution you can use right now. Other questions? One more question? Yeah. Yeah, so the question was, there are some very computationally heavy things that go on in Matplotlib that are hard to make interactive, and what would I suggest for that? Honestly, I don't know of a good solution right now. I was really impressed with the VisPy talk. If you want to go back and look at that, what they're doing is they have a high-level graphics framework that targets the GPU versus OpenGL. And there's just some phenomenal examples in there. And they're doing some of this really computationally intensive visualization. So it might be that VisPy is a way forward with that. And it might be, like I said, that, that we have to abandon Matplotlib and its architecture for this sort of large data visualization. I'm not sure about that, but there are some solutions on the horizon. Well, thanks very much. I'll be out in the hallway if you have more questions, and I appreciate the time.